All right, here's an example of actually calculating a Taylor series for a particular function. So we're working with the function e to the x. And so when we say that we want the second degree Taylor polynomial for it, we want to come up with what quadratic does as good of a job as possible of mimicking the function e to the x in the neighborhood of x equals 0. So I want to draw a picture down here. We've got our function that is e to the x. We're looking for the polynomial, the quadratic, that does something like this. So we want the parabola, that's a questionable looking parabola, but we want the parabola that does as good of a job as possible of mimicking what's happening in this function e to the x in the neighborhood of 0. Right? And to find this, we have sort of this formula for it. And this formula is set up so that it's rigged so that the polynomial that we come up with, this p2 of x, has the same derivative as our function f of x, e to the x, at the point in question. So this is rigged so that, so to find this, if we find the derivatives of e to the x of valuated x equals 0, we can use that to plug in for these components. So the derivative of e to the x is e to the x. This evaluated at x equals 0, so e to the 0 is 1. So f of 0 is 1, f prime of 0 is 1, f double prime of 0 is 1. This is all because the subsequent derivatives of f of x are always 1. So our second degree Taylor polynomial is going to be 1 plus f prime of 0, which is also 1, times x, plus f double prime of 0 over 2 times x. And that's it. So it's the polynomial 1 plus x, oh, I forgot a squared, 1 plus x squared over 2. So this function is the best approximation for the function e to the x. It's the best quadratic, it's best parabola approximation of e to the x.